Yeah, there was a follow-up that yes was the simplified formula that they were asking about. All right.
Now, I guess another comment to be made about that is the fact that today, and certainly in the examination conditions, your computational ability is considerably different than it was, say, in 1981 when that chapter was composed. There really isn't a great deal of excuse for not using rigorous formulas, because it's fairly easy for anyone, if they have the proper variables and everything, to do almost any formula calculation nowadays. And you can actually look at some of these formulas and look at the ways in which the different components of the formulas influence the answer, and to have some feeling for what sort of things could be rounded off or simplified. And one of the typical examples, as you'll notice in that chapter on mining surveying, is the radius of the Earth. If you look at the formula for meridian convergence as an example, it uses the particulars of the ellipsoid in the context of doing a geodetic calculation. If you're doing it in the other contexts, you may be able to just use an average value for R rather than going through the particulars of the radius of curvature of the ellipsoid and the direction of the azimuth and all this sort of thing. So as a professional, it's necessary for you to appreciate the rigorous approach and also the ability to appreciate when the rigorous approach can be relaxed a little bit.
All right, we have about 7 minutes remaining before the system kicks us out. We have a question. Can we have an explanation for study guide question number 12, please?
When we use an instrument to measure angles, we have a process of centering the instrument, leveling it, pointing, and then reading. So we have expressions for the effects of centering, leveling, pointing, and reading. If we look at the parallel process with the leveling instrument, we set up the level, we level the instrument, and then we point it at the rod, and then we take a reading. And when we're using a precision instrument like the VILD N3, the pointing and reading processes are together, because we move the micrometer to bring the crosshairs in coincidence with the graduation on the rod, and then take a reading of the micrometer. So my pointing and reading are together on it. The leveling ability of the N3 is that centering accuracy that's mentioned there, which is plus or minus 0.2 of an arcsecond, which then propagates directly onto a variation in the line of sight. When we use the N3 for a certain length of sight, and in this particular case, if the benchmarks are 20 meters apart, we assume, since we're not told otherwise, that we can set up halfway in between. So that means we have back sight and foresight lengths that are 10 meters. And when that's the case, the pointing and reading error is 30 seconds divided by the magnification, which is an angular amount, and that's propagated over the length of sight for one sight. So that means we have a plus or minus, say, 0.035 of a millimeter for a rod reading as a consequence of the pointing and reading variation. And if we take the 0.2 arcseconds in a similar manner and propagate it over 10 meters, it's plus or minus 0.01 of a millimeter. That's in one rod reading. Backsight minus foresight, then we take the two together by their squares, and that works out to be, sorry, I don't have it I have it also then multiplied by root 2. So you take the 0.035 squared plus 0.01 squared, add them together and take the square root, and that's the standard deviation of a single pointing on a single scale. So you multiply that by root 2 to get the back sight minus foresight, and then you divide by root 2 because we're averaging from the two scale readings. So that means that we end up with a back sight minus foresight determination of plus or minus 0.035 of a millimeter. If we're doing it for tilting, then we do that measurement a second time and take the difference. And that gives us a difference in the height difference. So like a delta H. So that means we take the 0.035 and multiply by root 2 again, and that gives us a 0.049, which is the standard deviation of the difference in the height difference. And that can then be made into the tilt by taking that and dividing it by the length, the horizontal distance between the two benchmarks, which is the 20 meters. And when we do that, it works out to be half an arc second, or yes, 0.5 of an arc second. So what we have now done is we have taken a geodetic measurement process with geodetic equipment and come up with a geotechnical data comparable to what a geotechnical instrument could probably do. And you wouldn't have a geotechnical tilt meter with a base of 20 meters. It would only be a few centimeters.
Well, if it doesn't, we've only got 2 minutes left, so either way. Yeah, I'm just trying to, we have a few questions and I'm just trying to get through them. There seems to be some question about time constraint and length of the exam. Would they want to be using the simplified formulas then, just so that they can actually get something down on paper?
Provided you explain the assumptions behind the simplified formulas.
I also got to expect an examinee to read the mind of the examiner regarding a drift not yet driven and then perform a rigorous calculation when a simplified version is supplied in all in 3 hours is ridiculous. Is this what needs to get done to get full marks?
I'm not so sure I could quickly answer that. I'd have to digest what the question said.
All right, we're just about to run out of time, so I am going to I will bring this to an end. I'd like to thank everybody for attending and for their excellent questions. I'd also like to thank Dr. James Secord for his very kind participation in this. As with the other ones, this will be uploaded on YouTube for your later review. And I'd like to thank you, and good afternoon, and enjoy the rest of your weekend.